With this video, we initiate a discussion of the integrated rate laws. Okay, before we do that, let's do a brief summary of what the rate law is. Suppose that we have a chemical reaction A to B products. What we know is that the concentration of A should decrease as a function of time as the reaction takes place. Okay, so if we start with a concentration like this, then this will fall in some fashion that we will have to determine. Okay? Now, we have defined the rate of this reaction simply as the speed at which the concentration of A decreases on time. That is our initial definition of the rate. And then what we've done is simply say that, well, there's going to be here a rate law that tells me how this rate changes as a function of the concentration of A. And this variation is simply this. Okay? Notice that we know that the rate should vary as with the concentration of A, because from this plot we can see that the slope right here is actually changing as the concentration drops. Okay, so the slope of that line happens to be the rate, the slope of this line happens to be the rate. Notice that those slopes are given by the change in the concentration of A as a function of time, the first derivative of the concentration of A versus time. Right, so something that we're actually going to do now is essentially put these two definitions of the rate together and then try to integrate it to be able to determine the following. Look, if we know the rate, which is the steepness of this curve at that particular point, then maybe what we can do is use that slope to be able to predict how the concentration of A changes as a function of time. Okay, so that's actually what the integrated rate law does for you. By equating these two things and integrating, you can actually find a functional form for the dependence of the concentration of your reagent on time. And that is extremely useful because you can come up with things like, well, how long will it take for the concentration to decrease to half of its original value, or how long will it take for the concentration of A to completely disappear, and so forth. Okay, so the integrated rate laws are actually very, very useful. Right, so in this video, what we're actually going to do is come up with the integrated rate law for a zeroth order reaction, which is the simplest case, and then we will see the usefulness of having that integrated rate law. Right, so the approximation here that we're making is that after doing some experiments, we have determined that this reaction order with respect to A happens to be 0, and this is a zeroth order reaction therefore. Okay, so then what that means is that actually the rate does not depend on the concentration of A at all. It's just going to be constant with time. Okay, so then what we actually do to obtain the integrated rate law is equate these two definitions of the rate. We know that the concentration of A, the first derivative of the concentration of A with respect to time is equal to the rate, but the rate can also be determined from the rate law, and in this particular case, for a zeroth order reaction, that is simply equal to the rate constant. Okay, so this is the rate law in a differential form. Okay, but the idea then is to actually integrate this to find a functional dependence of how the concentration of A changes as a function of time, so that we can actually trace this line accordingly. Right, so to integrate this is not going to be very difficult. We simply have to separate variables, concentrations on one side of the expression and then time on the other, and then carry out the integration. Okay, so I can separate variables by doing this. Okay, for convenience, I can change the sign right here and then the sign right there, and now I'm actually ready to integrate. Okay, so we're just simply going to integrate between the start of the reaction, where the concentration is equal to A sub naught, to any time during the reaction, to predict what will be the concentration of A after some time that we wish. Okay, and then the integration on the left hand side will be from time is equal to 0, which is the start of the reaction, to any time that we wish. Okay, time is equal to t. Right, so these are just simple integrals, right? So the integral of differential of A between A and A naught is going to be equal to the concentration of A that we have to evaluate between the limits of integration A and A naught Okay, and the right hand side of the integral is going to be the following. Notice that minus k is a constant, so you can come out of the integral. Okay, minus k, and then we will just have the integral of differential of t between t naught and t, but that integral is simply t, that we have to evaluate from t is equal to 0 to t is equal to t. Okay, so that is the result of the integral, and we just simply have to evaluate the limits of integration. Right, so to evaluate the limits of the integration, we simply replace this value into this function and then subtract what happens when we replace this value onto the function, right? So that will be the concentration of A minus the concentration of A at time 0. This is the result of the evaluation of the limits. And then on the other hand, on the other side, we'll have, this will be K, and then to evaluate the limits, we simply plug this value into this function and subtract whatever happens when we plug that value into this function. So that will be K times T minus T naught, which is equal to 0, because time is 0 at the start of the reaction. Okay? Alright, so we're ready to actually find a functional form for how the concentration of A changes on time for a zeroth order reaction. The concentration of A is going to be equal to the concentration of A at time 0 minus KT. Okay? Notice how beautiful this is. If you know the initial concentration that you started the reaction with, for example, half molar or 0.1 molar or whatever it was, and then you know what the rate constant is, then you can simply ask the question, well, what will be the concentration that I have after 5 seconds have elapsed since the start of the reaction, or maybe 10 seconds, or maybe 2 days? Right? There's a lot of power in this expression because it again allows you to see how this concentration is changing on time. Okay? So we can actually carry on and try to draw exactly how this line or how this dependence should look like. Notice that here we can plot A as a function of time. So we have this on the y-axis and that on the x-axis. You can clearly see that because this is a constant and that is a constant, this should be the equation of a straight line. Okay? It will be a straight line in which the intercept with the y-axis will be A naught and the slope will be minus k. Okay, notice that again what we're going to be plotting is this, and you have that that's what you're going to be plotting. This will be the intercept with the y-axis, and that is the slope. Okay, so we plot that line, and this line should be something like this. Okay, where the intercept with this axis, this is going to be equal to A naught, and the slope is equal to minus k. Okay, so this is the integrated law for a zeroth order reaction, which shows a linear dependence of the concentration of A as a function of time. Okay, so when we start the reaction, the way that A decreases on time is linear.